This is our second and last video for Chapter 10. We are going to cover sections 4 through 13 and the last two reactions in the chapter. And then I'm going to mention this again throughout the video, but we are going to skip sections 8, 9, and 12. In the last video, we looked at the chlorination reaction of an alkane, and I did mention that we can do it with other halogens. I even talked about that we can do it with bromine, but we're going to look at all of the halogens together and decide whether or not we can do the halogenation reaction with our other halogens. And so here are our four halogens. We have fluorine, chlorine, bromine, and iodine. And we're going to decide whether or not they can happen based off of the energy associated with the reaction or the enthalpy of the reaction. So as we look at this, we can see that fluorine has a negative 431 kilojoules per mole. So that's highly exothermic. In fact, it's so exothermic that it's actually an explosive reaction. Iodine is a positive 55 kilojoules per mole, which means that it's endothermic and it's too difficult of a reaction to complete. But chlorine and bromine are both exothermic, but small enough amounts that they are manageable, so that's what our halogenation reaction allows us to work with, our chlorines or bromines. So we're going to look at those two a little bit more closely. In the first step of the reaction, the first propagation step of the reaction, we do a hydrogen abstraction, and this is the slow step of the reaction for both of these halogens, but for bromine it's even slower. So for bromine it is actually an endothermic step, and then in that second propagation step, the halogen abstraction, it's approximately the same for both of them. And then overall they are both exothermic, but bromine is less exothermic because of that starting endothermic step. So what this means is that bromine's going to react a lot slower, and as a result, that means that it's going to become more selective. Here's our energy diagram showing us the same information. So we can see that it's a two-step reaction because we have two hills. And in that first step for chlorine, we have a small activation energy, and our intermediate down here is lower in energy, showing us that that first step was exothermic and that second step was exothermic. So overall, it is exothermic. For bromine, we have a large activation energy, and our intermediate is higher in energy, so that first step is endothermic, and then our second step here is exothermic. So when we talk about how reactive chlorine and bromine are, and I said that bromine is more selective, that's where this is going to come into play. When we look at a larger alkane, so we're going to look at propane here, we want to know how many possible products there are. And our halogen could add to that center carbon, and in order to do this, we have to take off a hydrogen. So there's two potential hydrogens that could be removed and replaced with our halogen. Either one would give us the same product though. Or we could take one of these three hydrogens off and replace it with a halogen. Now because this is a symmetrical molecule, if we removed one of these hydrogens and replaced it with a halogen, it would give us the same product as if we did it over here. So it's telling us up here that there's two hydrogens that are in the same type of environment, and there's 6 hydrogens that are in the same type of environment. So when we're deciding what our major product is, we're looking at statistics, meaning how many hydrogens are in that environment that could have been removed to give us our major product. And we're looking at radical stability. When we remove one of these hydrogens, it will give us a secondary radical, and when we remove one of these hydrogens, it will give us a primary radical. So when we react chlorine, because it reacts so quickly, we are definitely going to get both products, and they're going to be nearly equal. So this is a 60-40 split. And our major product, the one with the higher percentage, will be the one that came from the more stable radical, so the secondary radical. For bromine, the major product is the same, that secondary radical gives us our major product, but because bromine reacts more slowly, it can be more selective. So instead of getting that 60-40 split, notice that our major product is 97% and our minor is only 3%. So in the lab, this is a better option because it means we have less of our side product if this is the product we are trying to make. So let's do a practice problem. We are going to draw all of the possible products for the following reaction and then circle our major product. So when we're looking at a problem like this, we want to find how many unique hydrogen environments there are. So we have our carbon on the end here. We could add a bromine there by removing a hydrogen. We have our carbon here, and we have our carbon here, and we have our carbon here, and this methyl coming off of the chain. But both of these methyls are the same as one another. They're in the same environment, so that leaves us with 4 products. We're going to add a bromine here, 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 and then to one of these methyls. So here's our bromine added to that end carbon. Our bromine added to the next carbon in, our second carbon. Our bromine can add right here to give us this product. And then our bromine can add to our methyl on the end of that chain to give us our last product. Now to decide what our major product is, we want to look at our type of radical. So going to our carbons on the end, so either one of these carbons would give us a primary radical, so that's not going to be our major product. So this one on the end here, this would come from a primary radical, and this one would come from a primary radical. Our carbon next in line here would give us a secondary radical, and then the one right here that has both those methyls sticking off of it, that would be from a tertiary radical. So because that will be the most stable radical, that tells us that that will be our major product. One thing we didn't talk about in our last video when we looked at our first reaction is the stereochemistry of that reaction. When the radical forms, it is mostly trigonal planar. We can think of it as a flat structure. And because of that, our reaction can happen on either side of it, and so we can end up with both of the stereoisomers. So if we're creating a new chiral center, then we will end up with both the R and the S of our stereoisomers, so we'll get a racemic mixture. And if we already have a chiral center and we're adding a halogen to it, the chiral center that's a result will also be racemic. We will get the R and the S mixtures there. Next, we're going to look at reaction number 3. And yes, we did skip reaction number 2. We're going to do them out of order. Reaction number 3 is allylic bromination. So we're going to add a bromine to the allylic position of an alkene. And we can't just use Br2 or Cl2 for this because we know that Br2 and Cl2 will react with our alkene to give us a dihalide. We saw this in chapter 8. So instead, we're going to react our alkene with NBS. So its abbreviation is NBS. It is called N-bromosuccinimide. So this is what its structure looks like. And we are going to do that with some light or heat. We know we need that to help start our reaction, to do our initiation step, and some peroxide. And as a result, we will add our bromine in that allylic position selectively. So meaning only in that allylic position. We produce succinimide as a little side product over here, but in reality, we don't really care about that part. That would just get dumped into our waste container. So let's look at the mechanism for this reaction. The initiation step starts by breaking that nitrogen-bromine bond so that we can create our bromine radical. So this is how we get a bromine radical without using the Br2. And then our propagation steps look very similar to what we saw in our first reaction. We're going to use that bromine radical to do a hydrogen abstraction and we're going to create a carbon radical. But specifically, we've created an allylic carbon radical. That is why this hydrogen has been chosen out of all of the possible hydrogens on our structure. And then in the second propagation step, we're going to react it with Br2 to make that carbon-bromine bond and an additional bromine radical. So two things to point out here. We created that bromine radical, which can then go back and react with another alkene, keeping that chain reaction going. And second, we have Br2 here. Where did this Br2 come from? So we're not adding Br2 into the reaction, but because we're making these bromine radicals, they're going to combine together to make Br2 molecules. Because the concentration of them is so low, we don't have to worry about them reacting with our alkene. Now, when we look at termination possibilities, there's two that are going to be okay. We know that the bromine is going to react with the bromine and create our Br2 molecules that we need to use. We know that our bromine radical could just react with our allylic radical to give us the product we care about. The third termination product that could happen is that we could get two of these allylic radicals combining together to give us this termination side product. So I did label it as a side product because if this is our intended product, then this would definitely be a side product. So let's do another practice one. We are going to draw all of the possible products for the following reaction and circle our major product. So first, we want to look at what radicals could form. We're reacting our alkene with NBS and heat, so we know it's going to target those allylic positions. So we could remove a hydrogen up here and create a radical, or down here and create a radical, and we would get these two possible radicals. So the products that would form from these would be this one, so our bromine at that top position, or this one, our bromine at that lower position. But because we have an allylic radical, one of the first things we talked about is that they can be resonance stabilized. So we need to look at what these two structures look like after they go through resonance. So as we look at these two structures here, how we got there is we're going to take our radical, move it onto that bond, and we're going to split our alkene so that our two electrons will go one this way to create our new double bond, and then one over here to create our new radical. And we're going to do the same thing here. We're going to take our radical electron and move it right there, and we're going to take our alkene, one electron goes there, so we've created our new double bond, and then our second electron is going to go right there to create our new radical. So we've created two new radicals, and now we want to look at what products would form from those two. So we can get this one where our bromine is adding to this radical, or this one where our bromine is adding to this radical. And so we end up with these four products. Two of them were the result before resonance was applied, and two of them were with resonance. So what is our major product? So I'm going to give these numbers just to make them easier to talk about. If we look at where they came from, structures 1, 3, and 4, so that would be from this one, and this one, so 1, 3, and 4, all came from secondary allylic radicals, which are very stable. However, structure number 2 came from this tertiary allylic radical. So that means that structure number 2 would be our major product because it came from the most stable radical, a tertiary allylic radical. So I am going from section 7 to section 10. We are skipping 8 and 9. And this takes us to our last reaction in this chapter, so reaction number 2. And it is a reaction we've seen before. This is the anti-Markovnikov addition of HBr to an alkene. This was reaction number 2 in chapter 8. So we've seen this reaction before. We know we're going to add a bromine to the less substituted vinylic carbon and a hydrogen to the more substituted. So we're going to focus on the mechanism here. We have peroxide in there. We called this a radical initiator in our last video. That bond gets broken with our heat or our light, and we create these 2 oxygen radicals. And then the oxygen radical is going to do a hydrogen abstraction to create that bromine radical. And then we're going to do a step we haven't used yet, but we're going to use that alkene bond. And so we're going to make a new bond from that bromine and alkene electron, and then that second alkene electron is going to create our carbon radical. This step right here explains why it's anti-Markovnikov. The bromine's going to the less substituted side so that our radical can go to the more substituted side, giving us a more stable carbon radical. And then our radical will react with HBr, doing a hydrogen abstraction, so the carbon bonds to the hydrogen, and we create that bromine radical, allowing us to go through that chain reaction again. Termination step, this is one possible one. Again, anytime we do radical with radical. The next section is talking about polymerization. So a polymer is a large molecule of repeating units. So the smaller units are called monomers, and then when we join them together, it creates a polymer. So poly means many, mono means one. Polymers are used throughout our everyday life. A couple examples here are a soda bottle and its plastic cap. So the soda bottle itself is very flexible, and this is because the polymers that are used to create it are highly branched. So not just a string of carbons, but these branches coming off of the carbons. The plastic cap on the soda bottle is very rigid, and that is because it does not have any of those branches, and so it allows for a more densely packed structure. Those molecules can get together a lot closer because they don't have these branches in the way. Last section for us is putting this information together into multi-step syntheses. We haven't known how to react an alkane until this chapter because they are so very unreactive. But now we know how to add a halogen to an alkane. From our halogen, we know how to do a substitution reaction, we know how to do an elimination reaction, and then we also have another chapter, chapter 8, that tells us how to react alkenes. So this is opening up our toolbox and adding a lot of information to it. So we're going to do 2 practice problems before we're done today. We're going to do 2 multi-step syntheses. So we're going to propose a multi-step synthesis to go from this alcohol molecule to our bromine molecule. And you guys know I like to do a little bit of inventory. So we have 1, 2, 3, 4, a 5 carbon chain with an alcohol on number 2. 1, 2, 3, 4, a 5 carbon chain with a bromine on carbon 3. So as I look at this, I know obviously I need to get rid of my alcohol, but I also know that I need to make this carbon a reactive carbon in some way. So there's a couple different ways to approach this, but here's how I'm thinking about doing it. I'm going to start by doing an elimination. So in our substitution elimination chapter, chapter 7, we know that we can get rid of an alcohol with some acid and heat and create our alkene, our most substituted alkene. Now if I want to add my bromine right here, that means I need to add it using anti-Markovnikov techniques. We know how to do that. Now we know how to do it from 2 different chapters. So I'm going to use HBr and a peroxide, and that will add my bromine at that less substituted position. Okay, let's do one more. We're going to start with a cyclohexane, and we're going to create a cyclohexadiene, so having 2 double bonds within that structure. If you're ever given an alkane to start with, no functional groups, no halogens whatsoever, you really only have one choice. We have to start with this reaction. It gives us another reactive point, because now once we have that halogen on there, we know we can do substitution and we know we can do elimination, so it opens it up. If I want to create a double bond and I already have a halogen on here, I can do an elimination to get the first double bond in place. So I'm going to use a strong base to do this. I'm going to use methoxide, or as students like to call this, Naomi. So we've added Naomi, we've added in our double bond, and now we need to get a second double bond on there. So really, again, that means we have to react a carbon that isn't reactive at all, but luckily it's in an allylic position, so we can use our NBS and heat to add in that bromine onto that allylic position without affecting the alkene that's already present. And then our last step is we're going to repeat that base addition to do another elimination so that we end up with that second double bond. And we know the double bond will go to that direction. It can't go over here because the bond angles of that ring won't allow to have 2 back-to-back double bonds, or 2 accumulated double bonds as they are called. Alright, that is it for chapter 10. Thank you very much.